Okay, in the circuit below, what should the resistance of the variable resistor RL be set to maximize the power delivered to the load? So first, we know the power is the rate of transfer energy, and I can calculate it using any of these equations here. I'm going to focus on this one here. So the power depends on the energy transferred per unit charge, which is the voltage, and how much charge is flowing past per unit time, which is the current. So in this circuit here, let's look what happens if I increase the resistance. Now if I increase the resistance, the voltage here, the terminal voltage will go up and the lost PD will go down. So that means that we would expect the power to increase. But the problem is, if you increase the resistance of the load, you're also making the total resistance larger. Now, if you make the total resistance larger, you're going to decrease the current in the circuit. So it turns out it's going to be a fine balance between the current and the terminal voltage here. And you get a maximum power delivered to load at this particular point here. It turns out this is when the resistance of the load is equal to the resistance of the internal resistance. So in this case, when this is equal to 3 ohms, that's when you get maximum power transferred to the load. Okay, so to summarize, the power delivered to the load is maximum when the resistance of the load is equal to the internal resistance. Okay, so we're going to show that the power delivered to the load can be written out by this equation here. So firstly, we know power, you can use any of these equations here. I'm going to use P equals IV. So the current to the load, I'm just going to use Ohm's law for the whole circuit. The total potential difference, which is the EMF, divided by the total resistance. That gives me the current through the load. I want to figure out the voltage, the terminal voltage in this case, the load voltage across the load. So I'm going to use the potential divider equation. I'm going to take the total voltage, which is the EMF, divided by the total resistance. So I'm chopping up into total resistance and multiplying by R to figure out how much of that fraction of that total EMF goes across the load. Put these into the equation there for I and V and multiply it out. I get this equation. It looks quite complex, and that's what gives us this graph here with the power of the load on the left hand side on the y-axis and the resistance of the load on the y-axis. And it turns out if I set R is equal to internal resistance R, I get a maximum value for the power.